Yeah. So for starters, we have this diagram, pressure versus temperature. So as we start, whenever we have one of these, we want to label our different regions. So we already went through this. So you have our vapor, liquid, solid region. This is a fairly characteristic diagram. And then we have all these lines in here. So we have our solid liquid line, our liquid vapor line, and our solid vapor line. So now we have a sense of where everything is on here. What was question 1? Let's see. Oh, I forgot. We have our critical point as well. That's kind of a key landmark. You want to label every landmark on here. So they didn't just get bored and stop the line. This is where you get a key thermodynamic state, the critical point, where the liquid and vapor start to get skewed with each other. And then we also have our triple point here, where you can have all 3 phases at once. So that's all of our key landmarks labeled on here. So we have path 1 right here. We see it starts in solid land, continues on through liquid land, and goes all the way through vapor land. So that's kind of 3 really important pieces of information to start with. And we know it stays at 20 atmospheres the entire time. So this is our first diagram. Then we have the totally different diagram, but it's actually almost like the same diagram, but a different angle. It's pressure, but specific volume, but it is the exact same system we were just dealing with. But as you can see already, it looks very different. So let's go through and try to make the same landmarks labeled and see how it varies with this. So I'll ask you, let's see, what do I start with? What's this over here? Gas? Liquid? I heard both. Vapor? More vapor. Okay, that's vapor. What about, well here, let's just go through. So yeah, so that we have vapor, and I already gave it away here. So here is our liquid right here, and then here on the far side is solid. Now you see, unlike the last one, we have lots of not colored areas. Why is that? What's going on here? Does anyone know? Nate?
We have the coexistence of liquid and vapor.
Yeah. So just like on phase diagrams before, where we've had a 2-phase region and it can split up, that's exactly what's going on here. If you put a point here at 1 atmosphere, it's going to split up into your 2 phases. On the diagram we were just dealing with, these regions were represented by a single line. The liquid vapor region was just a single line going down the graph. And if you were moving across that line, you weren't actually moving anywhere on the temperature pressure graph, but you could still be moving around in that 2-phase region. We can see that here, and that's because when you're dealing with volume, when you're compressing, vapor has a much larger volume than liquid. So it's something you can actually see on this graph. So let's label those regions here. And then we know we also have our critical point. So that's when we get up here, when we get high enough in pressure, it kind of blurs the line between our liquid and vapor region. And then we know we also have a triple point. But it's less of a point in this case now because of equilibrium just kind of extending out. So this is where we have all the regions kind of hitting. So we have this diagram slash real world example to show you. So this is the exact same system we're looking at, but this is a 3D representation. So you can get any of the graphs that we've shown up there just by looking at this. So everyone can kind of see, what is this a graph of? Is this the first or second graph we saw? Let's see. Yes. So you can see kind of all these features if you look at it from a 45-degree angle. But as soon as you start looking at it this way, all the features on this side get obscured. And all you can see is this region, and this region. You have your solid, your liquid, and your vapor. Now what happens when I turn it this way? Yeah, it's this graph up here. All of a sudden this all becomes available. And that's our liquid vapor right here. When you have it like this, you can't see any of that, and that's why it was represented just by a single line in the other one. And then you also have this little divot right here, which represents our liquid solid line right there. So depending on how you look at it, you can get a lot more information. Now, just like that, I can show it to you this way. Which graph is this? Yeah, it's the third graph. So we don't actually have that graph, but if you wanted it, this is what it would look like. And that would be your specific volume versus your temperature. But with a 3D like model of it like this, kind of all three are available to you. And you can see different kinds of features looking at any given one. So let's continue with our path 1. So we know that we were at, 20 atmospheres. So that's right here. And we know we did solid, liquid, and vapor. So we can kind of label where all that falls on here. We have our solid, liquid, and vapor there. Now we know that it's probably not going to just jump straight across. So we can fill in the blanks here. We know we have to transition from solid to liquid and liquid to vapor. So that's what, like, the points in here that we didn't quite see on the other diagram are. So that's how you kind of transition to this. But it's all about finding your key landmarks on both graphs. And then sometimes you can just connect the dots from there. So, and then it also wanted us to label A and B. So it wanted the liquid side of the solid-liquid equilibrium at point A. On the other graph, the point, kind of stretches this whole region, but that's why it has to specify that we want the liquid. So A kind of spans this right here, green part, and then we can just read off, if we know we're on the liquid side, read off the specific volume. And then we can do the exact same thing for B. Point B on the other graph spans this whole region. We once again want the liquid side, so we go over to here, to our liquid region, read down the specific volume. Are there any questions on that first part? Have one. Maybe a question?
Well, I don't think this was, we didn't need to calculate the endpoints of like where we started and where we finished on that. I think it was possible.
What?
I don't think it was possible. I'm just wondering.
Yeah, was it possible to find the endpoints given the information in the problem of path 1?
In the vapor?
Well, I guess in the vapor you could have found it because
Yeah.
you're told it's an ideal gas, but maybe
How
not.
far do you think it goes?
Let's see. I don't remember what the numbers you're giving.
About this far.
I don't
Put
know
your
this
thumb
far.
up there. Yeah, right about there is where it ends.
Okay. So yeah, so that's something you didn't necessarily, I didn't ask you to figure out, but the main point is you know that it stretches between the three regions, solid, liquid, solid, liquid, and vapor. So that's something you could like though, because you're told it will behave like an ideal gas. So let's jump back to our very first diagram, and now we're going to consider path 2. So we know path 2 starts with the liquid, where this is our liquid region. And it goes down at a constant temperature of 150 degrees C until it gets to, let's see, it's the liquid equilibrium, liquid vapor equilibrium at 2 atmospheres, and then it keeps going. So once again, let's note like these key landmarks. We have a section in the liquid, and we have a section in the vapor. So now let's come back to our other one, and so. Take the information we know. We know that it hits at 2 atmospheres. We know that it hits liquid vapor equilibrium. So that was a point on the other graph. But now on this graph, we can go to 2 atmospheres. We know this is like the equivalent to that equilibrium point on this line, and we can just draw that in for starters. So that's one landmark. Then we also know that we have the liquid on the other side. Now, in general, as when you're changing your pressure. Liquids are generally incompressible. So we can assume that the specific volume that we're at on this side of the equilibrium when it's all liquid, if we change the pressure, we can most likely just stay at the exact same specific volume. So on this diagram, it's also just you're just gonna make a vertical line from there. So we can, and we know we started at 100 atmospheres, so that fills in these 2 points. As long as you know it's a straight line, you go from 100 to this point. That's all you need for the beginning part. Then also, it wanted us to find point C. We knew that was at equilibrium. It specified we wanted the vapor side of it. Same thing we did for part A, just read it off. Once you know where you are on the map, all the information is available to you. So then we had one last part. We know we go into vapor at this point, so we're going to have to be stemming off from this line. So we are told that it will behave like an ideal gas in here, and we know what pressure it goes to. So if we look at our ideal gas equation, and then we realize that we have a log plot going on here, we can just convert our ideal gas over. We want things in terms of the log of the specific volume, and we want things in terms of the log of the pressure. So if we just take the log of our P equals RT over specific volume, we get log of P, and then if we just use some of our little math equivalencies here, we get minus the log of V plus log RT. Hopefully that's clear how you separate that out. And then so this kind of gives you like y equals mx plus b here, just a regular linear equation. Log p is your y, log v is your x, and there's a slope of -1 here. So from this point, you can just take that slope of -1. And so you can kind of see like these boxes that form. So like a slope of -1 would just be straight across the diagonal like that. So you follow that same slope until you get to your final pressure, which was 0.01 atmospheres, and there's your last line. Then it wants us to get point D, which we can just read off the pressure on that line, read off specific volume, and we have everything we were asked for. So that's all. Any questions on this? Anything on this, or if you want to see this 3D model again?